Okay, so let me recapitulate what I finished yesterday. So recall the definition of Shimura datum. So this is a pair Gx, where G is a reductive algebraic group over Q, and X is a G of R orbit of H in arm of the Deligne torus to G. And the axioms are, we ask that such a pair satisfies the following axioms. SD1 is that if you look at the Lie algebra, then it gets a Hodge structure through this edge, and for any edge you ask that you only have types -1, 1, 0, 0, and 1 minus 1. So the first axiom. The second axiom was that you asked that the inner conjugation by h of I is a Cartan involution. And the third axiom was that each time you have a direct factor in G add, then if you look at the projection from G to these direct factors, then it's non-trivial. This means that the set of R points of H is non-compact. Okay, so and now a Shimura variety. So a Shimura variety was obtained as follows. It was, so we started with Gx Shimura datum, and you fix K in G of AF, a compact open subgroup. And then you can consider, you define the Shimura variety associated to this data as the following space. So you take the quotient of x by g of the finite address over q divided by k, and then you take the diagonal action by g of q. And I gave the analysis of that space. So we showed that this is also the same thing as fix a positive an irreducible component x of x that I denote by x plus. And let's take its stabilizer inside g of q that I denote by g of q plus, and then still take the diagonal action of this. And once this is written this way, you see that this is a finite disjoint union for all g in g of AF over k divided by g of q plus of quotient of x plus by arithmetic group, which are image of congruent groups. So the important thing is that this set is finite. So this is really a space of finite type. And gamma g by definition was g of q plus intersected with gk g minus 1. Or more precise, this is the image of this group, image inside the joint group.
So can we just one example of like the SP
What? No.
No, I mean I was wondering. So if you have like Ziegler-Abelard space model of the full symplectic group.
Yeah, so okay, in general, you will not take Ziegler-Abelard plane, you will take the two copies and take the general symplectic group, because then you have a Shimura data. For example, there are no Shimura data associated to SL2. You only need GL2, okay, or PGL2, but not SL2. So that does not exist. So there are some subtleties here. And I mean, this K is just useful. If you want, you could just work with those quotients, if you prefer those quotients. The entire point of this complicated definition will be that this thing will be canonically defined over one unique number field independent of K. So in some sense, the invention of Deligne, I mean, Shimura was working with those things and trying to construct a canonical model of a sum field, but of course the field depending on gamma g. Deligne's construction, he just put together the different conjugate. And this is exactly what this construction is doing. So all these guys will be defined over some number field, and the number field is fixed, it depends only on gx. So I will come to that. But okay, so the geometry is really here, the number theory is here. That's the point. Okay. So as I said yesterday, so this tells you that this is a finite union of Keller manifold of finite volume. And well, if K is sufficiently small, at least, and the technical condition is called K neat. Well, I don't. K neat implies that all these guys are torsion-free, so you get manifolds. I don't want to give the definition here. The next step is to prove that these are algebraic varieties, and as I said, this is a theorem of Bailey and Borel in 66 that says that this space is the analytification of a smooth quasi-projective variety of a C. Not only this, but in 72, Borel proved that this is a canonical structure in the sense that it's universal. It's unique up to unique isomorphism in the sense that each time you have an algebraic quasi-projective variety and you take an analytic morphism from its analytification to that space, then in fact it comes from an algebraic morphism. Okay? So really this algebraic structure is unique. Okay, so let's say a few words about a very trivial case, zero-dimensional Shimura varieties. So this is a case where G is a torus. And then each time you have a morphism from S to TR, this defines a Shimura datum, just T, and then X plus is just 1 point, age. Okay? And so this means that if you fix a compact open subgroup in T of AF, K, then you get the Shimura variety associated to this, which by definition is a T of Q acting on H times G of T of AF divided by K. This is just a point, so this is isomorphic to the following finite set. Okay? This is what is a zero-dimensional Shimura variety. Okay. More generally, it might be interesting. Well, I will not do it here. It takes too much time. So, so for tori, it's just a finite collection of points. Once you have this, you can ask the general question, what are the connected components of those things? So connected components. Of course, in the case of torus, I mean, this is exactly the variety itself. So, well, it's just this set. What else do you want to say? I will come to the arithmetic later.
Sometimes you can say more about the finite set than its finite set.
Yeah, so I will come to that because, of course. Okay, so no, this is, well, I'm happy with this one. On the other hand, I'm not happy with this with the natural result that you get here. If you look at this, then I'm not happy because it tells me that this is this set. Okay, and with this one, there is a big difference with the other one. Well, apparently, except the notation, it does not seem to be very much different. Okay. Well, it is, because pi 0, after all, has to be an abelian group. And here it's obvious that this is an abelian group, but here it's absolutely non-trivial. Right? G is non-abelian, so right? And it's given here because. Okay. So how do you prove that this is really an abelian group? Well, there is a general formula by Dolly, but it's quite complicated. So I will make a simpler assumption that explains really what happens. So in the case, I will assume case where you take the derived group of G, and I will assume it's simply connected. Well, let's look at the following diagram. You have the derived group inside G, which goes to what we call T, the quotient. So T is a torus. I recall that the derived group is a guy generated by commutators. So it is semi-simple inside the reductive group, and the quotient is a torus. And I have another thing, which is the center, and going to the adjoint group by the adjoint map. 1. So I have two tori, and when I put together those two exact sequence, I get exactly, well, let's forget about the G here. I get that this map from Z to this torus is surjective, and there is a finite kernel. So you have to think of the case where you have SLN inside GLN, and here you have GM. Here you have 1 goes to the center, which is GM, goes to GLN, you go to PGLN, and 1 goes to G and to mu n, goes to GM, goes to GM, where here you take the power, the nth power map. Okay? So this is just the abstract formulation of this. And well, what is the result? The result is that assume that the derived group is 1 connected as an algebraic group. Then this implies that if you look at the following natural map, so you have the Shimura variety. Then you can do the following thing. So, well, let's write it directly this way. And yet then you can project it to T of AF. And then T of Q, and I will put a dagger here. So what is the map? The map is to an element xg. You just associate nu of g, the class of nu of g, where nu is this map. Okay. Then I claim that this induces an isomorphism on pi 0. Okay, so now I just have to tell you what is this T is the dagger, where, well, if you want T of R dagger, by definition, this is the image of Z of R to T of R. Okay, and T of Q dagger is T of R dagger dissected with T of Q. Okay, so it tells you that the set, this theorem tells you that the set of connected components is almost a 0-dimensional Shimura variety. Okay, so in some sense you have to think that this is kind of vibration theorem. It tells you that this Shimura variety, you mapped it to its pi 0, so this is almost, and in fact you can improve the general definition of 0-dimensional to make it a 0-dimensional Shimura variety. So the set of connected components is a Shimura 0-dimensional Shimura variety, and the fibers are essentially connected Shimura variety. So I don't want to enter into more detail, but it's a very nice geometric picture. Okay, so what's the next step? Well, the next step is to go to the limit over K. Namely, I define as being this Shimura variety without any index k as being the limit over all k of sjk of gx. So in which category do I take this limit? Well, these are quasi-projective varieties over C, and the transition morphisms are affine. So it makes sense to take the inverse limit in the category of scheme. So this is a scheme of a C. It's not of finite type. But Mill proves that it's locally Noetherian and regular. So it's a very reasonable scheme. And what's the point? Well, we can try to compute its C point. So let's compute the C point. Let's start with SHJK GX. I will just write it a little bit differently. So by definition, this is this space G of Q, take quotient of X times thing. But I will write it this way. Well, I have the center of G, and clearly the center acts trivially on X plus. So I can do the following. This is also X times G of AF times Z of Q K. Okay? Well, once more, this is the diagonal action. Now, notice that K is compact open, so it does not change anything if I replace Z of Q by its closure in the adelic topology. So this is also the same thing as G of Q divided by Z of Q, X times G of AF takes the quotient by Z of Q bar times K. And now you take the limit over all K's to get the C points of this scheme, And in fact, it works. And the general answer is the following theorem that the C points of this scheme are exactly the following. You have G of Q, Z of Q, and then you take the quotient of X times G of AF. You can just erase the K, but here you have to put a bar. So, well, under certain assumptions, in fact, in the case where Z of Q is discrete in Z of AF, and it happens many times, then in fact you get the simpler formula that this is just this, which is the initial formula you would like, but in full generality this is not true. Okay? But it's a detail. What is important here is that you see that this space acquires a right action by G of AF. Okay? And so you get a G of AF action on this space. And it induces the fact that, in fact, at finite level, you are just the quotient of what happens upstairs divided by K for this action. So in some sense, the nice object is really at the limit, but of course, we are not so much used to work with schemes which are not of finite type, so usually we don't like that, and we work at finite level. So this action induces at finite level Hecke correspondences, which are algebraic correspondences. Z of Q is the Q points of the center. Z is the center of G. So it acts trivially on X, so that's why I can put it on the right. It's a closure of Z of Q in G of AF. Yeah, I'm sorry, for the adelic topology. So you don't see anything. Dulin sees everything, but I don't see anything in this closure. Yeah, so usually, I mean, in the nice cases, as I said, Z of Q is discrete. So that's fine. But there are cases where in fact, if the anisotropic part of T is non-trivial, then it's not discrete. And, that's life. I shouldn't have erased. Well, this action induces the Hecke correspondences. So what are these? Well, fix any element in the finite adels, and then you look at the diagram. You have your Shimura variety. Then you have this cover. And then you have this right action by G of AF. So we can multiply on the right by G, and now you can go down to SHK prime for any K prime. And this gives you an algebraic correspondence between this space and that space, okay, that I denote by TG. So this correspondence, I call it TG. And of course, it's a nice way of defining it, but you can see it at finite level as follows. You start with your space at finite level. Then you go to the following guy. I never know the order. J key, J minus 1. GXC, and then you reproject after multiplication on the right by G to SH K GX K prime. Yeah, it was K prime if I want to put K prime. This is the same thing. We can also define this correspondence purely at finite level, obviously. Okay. So now, with all those definitions, what are special subvarieties? Well, we say that Z in CHK GX algebraic irreducible C is special if there exists a morphism of Shimura data and an element G in G of AF such that Z is the image irreducible component of the image, irreducible component of image of the following morphism. So I map my Shimura variety. So this morphism of Shimura data induces a morphism of Shimura variety. I translate by G. And then I project at finite level. And I look at the image. So it's just the abstract way of saying that, well, essentially you are just taking a sub-Shimura variety by your morphism given by your morphism of Shimura data, but you're allowed to take Hecke correspondences. Okay. Of such a what? Well, okay, I don't know what you call more concrete, but suppose, for example, that you have SL2Z, you have H over SL2Z. Then you take any element in SL2Q, which is obviously an element. But this is the same. This is essentially the same, except that I'm doing it for all the components at the same time. You mean you have approximation theorems that tell you that essentially this is the same procedure, you see. So I don't want to enter into the detail, but you have, I mean, this is the right picture.
Yeah, why don't you finish this up?
Because I really ask here at the level of of this compact open subgroup of the headers. I could do it on each component and pick, okay? It's still, yeah. I mean, the point is still that later this thing will be defined over a number field, and these Hecke correspondences will also be defined on the same number field. If I do it component by component, this is not true. It will change. Okay, that's. So note. No, come on. You know what is a classical Hecke correspondence for the modular curve. Yeah. You have to know. This is impossible otherwise. You just go to finite level by taking finite index subgroup, translate, and go back. Okay? Yeah, finite congruence subgroup. And no? Let's stay vague.
But at least I could do
no, I mean,
one for myself.
no, you have H over SL2Z. Okay, so now you take a congruent subgroup gamma in SL2Z, which means you reduce it, for example, mod P, and you take the kernel. Okay, and then this means that you have a map from H to this guy. Okay, and then I can translate by some element in the commutator of this. So I can, for example, put this to H modulo gamma intersected with G gamma G minus 1. Okay, and push it back down by translating by G. Okay, and so on. So I don't want to write all of them. So what I wanted to say here, the note is that the special points correspond exactly to morphism of Shimura data where G prime is a torus. Okay, so points correspond to the case where G prime is a torus. Yeah. But special points with this definition, and you see that these are CM points in the definitions that I gave yesterday. So these are equal in the case of Shimura variety. Okay. Well, and now the exercise is to check that this definition corresponds to what I defined yesterday as being special subvarieties associated to variation of a structure. In this case, you take any faithful representation of G. This induces a variation of art structure on X plus. This is what I explained yesterday. It descends, because everything is equivalent, to a variation of art structure on this Shimura variety SHK. You can define the notion of special subvariety for this variation of art structure, and you see that exercises correspond to this definition. Okay. Okay. So the next remark, and this is not obvious, is that special points are dense. Even for the usual topology in SHKGX. Well, this is almost obvious, except that you have to find one. Once you have one, you just take a G of Q orbit. Essentially, it will be dense. I mean, the G of Q orbit, as G of Q is dense in G of R, it will imply that all the special points, which are the orbit under G of Q of these guys, are dense. But you have to prove that there exists one, and this is non-trivial. You have to do it, but this is true. Special points. Yeah, but this is not enough. Of course, you have tori inside G, but you need the map edge from S to G to factorize through the torus. And this is not obvious that there exists such a T in the conjugacy class that you have chosen. You see, that's the point. All right, so let's go to canonical models. Oh, yeah. Yeah. Special points. So by definition, special points will be special subvariety of this type, but I ask them to be of dimension 0. But the unique case where the image of this will be of dimension 0 will be when this is of dimension 0. But now if you look at the definition, this will be of dimension 0 if only if G prime is commutative. And as it is reductive, it has to be a torus. So that's the link. Yes?
When you say dense, you mean dense?
Dense for the usual topology.
Oh,
Yeah. Yeah. All right. Okay, so now the serious business, canonical models. So what's the point? You want to show that all these things are defined over a canonical number field independent of K. So I will first define the field. This is called reflex field. And even the definition is not completely trivial. So the result will be that, let me write it this way. This scheme not of finite type, with its action of G of AF, everything will be defined over EGX, which will be this reflex field. So I have to define it and explain how you construct this model, which is completely unique. Okay, how do we do that? Well, you fix an element in X. So this is a morphism from S to G. And you look at the composite. Recall that you had this principal co-character from GMC to SC. So this was my mu. And here I'm going to GC. Okay? So this guy was A goes to A1. SC is just GM times GM. Well, the definition is that EGX is the field of definition of the conjugacy classes. The field of definition of the conjugacy class of mu H. So, well, very good. What does it mean? This means the following. Now I will use what I said yesterday again. So I have a map from a torus over C to GC. So everything, I mean, both sides are defined over Q, so let's look at the variety over Q. So you look at hom of GMQ to G. So as I explained yesterday, this is a functor which is representable by a smooth Q scheme. And also yesterday I explained that the connective components are G orbits. Okay? So this means that if you look at the quotient, this is an étal Q scheme. Okay, so this is just a disjoint union of spec of number fields Fi, where Fi over Q is finite. Okay? And so now look at this guy. Let's call C, C is equal as the conjugacy class of mu H. So this is a point. So C is a point of this variety. So this is a map from spec C to this guy. Okay. So E is just the residue field of that point. So E equals the residue field of that point. And what else? Well, because I wrote it this way, this is canonically embedded inside C. So this is a number field, because my scheme is eta over Q, but it's canonically embedded inside C. So this is really given this way. So some facts about that field, I won't say more about that. You can prove that this field is either totally real or CM. Okay. What is important is that suppose that you have age x age, a sub-Shimura datum of gx. So this will be used all the time. Then egx is contained in e age x age. Okay. So the subvarieties are defined over a bigger field. The second thing is that this egx, you can in fact compute it as a composite of the reflex field for the adjoint datum and for the torus T that I defined. So for the adjoint datum, for adjoint groups, this is a purely combinatorial computation on Dynkin diagrams. It depends on nothing. And so for the torus that you get T, I mean, this is a CM torus, and it will depend on the CM type. So in principle, this is feasible computations. Usually, this is terrible. But for example, for moduli space of Abelian varieties, usually, I mean, this is Q if you take GSP. So in many cases, it's simple, and in all practical cases, if you really need it, you can compute it. Okay, so this gives you the field. Now I have to explain you the structure, schematic structure of this field that you can put. So what we will do is that we will do it for tori. So canonical model when G is equal to T. Okay. So in this case, well, my scheme over C is just a finite collection of points, and what I want is to put a schematic structure over this reflex field. Okay, so let's do that. So I have my S to T R, where T is my torus, and so I get my Shimura datum, which is trivial. TH is a Shimura datum. Yeah, it's also Q. Then I want to compute this field in this particular case. Well, here everything is more simple because T is commutative, so I don't have to take orbit under conjugacies or trivial. So I'm just looking at that guy, so TC, and of course this is the same thing as hom GMQ bar to TQ bar, and so this is nothing else that the set of co-characters of my torus T. And on this guy I have my gal of Q bar of a Q action. Okay, defining my T torus, my torus T over Q. So this means that if you look at these hom varieties that I defined, well, this is just the étal Q scheme corresponding to this action by permutation of the Galois group on this set. To this. And E is just the residue field at mu H, which is in this. Okay, so in particular, this means that originally I had this mu H here, and now mu H is defined over E. So this gives me a morphism from GME to TE. Okay, where E is my reflex field. So on the other hand, what we know that the Shimura variety I'm looking at is nothing else than quotient of T of AF by T of Q, by the formula that I gave. The closure of T of Q in T of AF. So now what I want to define an action of Galois of Q bar over E on this. And this is the first thing, but not only this. I want it to commute with the action of Hecke correspondences, which are given by T of AF. But this space, I mean, the action is transitive. So I want a Galois action of gal of Q bar over E on T of AF, T of Q bar, commuting with T of AF. Then there is no choice. This means that this has to be given by a morphism from gal of Q bar over E to T of AF. Okay? And this is what I have to define. And conversely, if I define such a morphism, then it's obvious that this will define an E structure on T of AF over T Q bar. Okay? Okay, so I'm reduced to doing this, but this is class field theory. Class field theory will do it for me. Because you see, I have to define a morphism from gal to this torus. So it will factorize through the maximal abelian quotient. But class field theory describes exactly this maximal abelian quotient of the Galois group. So let's ab over E ab over AE be a maximal abelian extension. And so I will denote by gal of Q bar over E ab. By definition, this is the gal of the E ab over E. And so I want to define a morphism from this to T of AF. So how do I do it? Well, by class field theory, it tells me that this thing is isomorphic to the ideals of E. And then I take the quotient by what happens at the infinite place R. Divided by the closure of E bar. So now I see that essentially I'm reduced to constructing a morphism of groups from this to this. Okay, and well, so this is Artin reciprocity. So now let's just do this. Notice that you have the following construction. You take the multiplicative group over E, but you look at it as being a torus over Q. Okay? And then you take the restriction of mu H. This gives you a map to restriction of scalar from E to Q of TE. And now from this, you have a norm map, like for any restriction of scalars, of something abelian. So you go to TQ. Okay, so now take the AF points of this, and you just get this morphism. Which defines you the Galois action. Okay, so this is the explicit construction of the canonical model in the case where G is a torus. And this is the only thing that you have to remember is that this is more or less tautologically given by class field theory and the theory of complex multiplication. Now, what is the result? The result is that if you fix any Shimura datum and you look at its reflex field, then there is a unique structure of scheme over the reflex field of the corresponding Shimura variety at infinite level, such that the action of G of AF is also defined over this number field, and such that for any morphism of Shimura data associated to a torus to the Shimura datum Gx, then the morphism from the corresponding Shimura variety is defined over the reflex field of the torus. So, is it clear what I'm saying? In some sense, I'm using the fact, you just use the fact that the special points are dense in the Shimura variety, and you have fixed the canonical models on all those points. And the result is that this is enough to interpolate the structure, the algebraic structure, for the entire Shimura variety, knowing what you want on the special points. This is basically the idea. And this is what is called the canonical model, and the proof is due to Deligne, but not in all cases, and it was completed by Milne and Borvoy.
So that's a finite set, and so which Galois prefix?
So, no, you see, what I'm saying is that what I want to do is to define a Galois action of Q bar over here. And I said that because the action is transitive and I want this Galois action to commute with the action of T of AF, it has to be given just by a morphism from here to here. And now I construct this morphism from class field theory.
But I mean, coming up to the Galois.
Yeah, I pretend that everything descends. So you have to just check that it goes to what you want. When you take the quotient by T of Q bar, it kills the rest. Because here, you see, I mean, I take, okay. Here, this is really the finite thing that you want. Here, I should put the F if you want. But, okay. Okay, that's, yeah, I'm very late, so this finishes what I wanted to say about Shimura variety. So let's go to the Andre-Oort conjecture. So this is a special case of a conjecture I mentioned yesterday. So, but this is of course what is called the Andre-Oort conjecture. So you have the GX Shimura datum, and you fix a compact open subgroup in G of AF, and so you have the associated Shimura variety, and you give yourself a set of special points. Recall that here these are really CM points. In this variety, and then the conjecture of yesterday gives you the following: every irreducible component of the Zariski closure of the union of those points is special. Okay, so I explained the simplest case of this conjecture in the workshop, so maybe I can repeat it. So the simplest case is the case where G is SL2 times SL2, and so you look at SL2R over SL2Z and SL2 times SL2 of Z. So by the J invariant, this is isomorphic to C times C. So this is your Shimura variety. And the special points corresponds to pair of special points τ1, τ2, which are in image. So this is given by the J function. And you are in the upper half plane, and you take imaginary quadratic guys. Okay, these are the special points. And now the question is, well, it's easy to describe the special curves. As I said, you have horizontal and vertical going through a special point. So suppose this guy is special, or this guy is special. So those curves will be special for trivial reasons. And you have other ones which are given by isogeny between elliptic curves. Okay, embedded by the two projections on the two factors. And the claim is that if you have any irreducible curve in C times C that contains infinitely many such doubly image of imaginary quadratic points, then this is one of these curves. Okay, so let's give some history. Maybe I will not write it because it takes a lot of time. So this conjecture was done exactly in that case by Andre in '89. Then Oort made a similar conjecture, but he was interested in subvarieties of the moduli space of abelian varieties, principally polarized abelian variety AG. And then the first result started with Moonen's thesis in '95, where he proved it under a very strong assumption about the points reduction mod P. Then Edixhoven proved that case under GRH in '95. Andre himself in '97 proved it unconditionally. Then Edixhoven and Yaffe proved the case of curves inside any Shimura variety under GRH. So if you suppose you have a curve inside any Shimura variety containing a Zariski dense set of points, then it has to be special under GRH. Then there was for the GRH for Dirichlet L functions. So Clausel, Ulmo, and Ulmo in 2005 produced some equidistribution results which are related to that problem, and I will talk about that in a minute. And then there are the two main recent results. So theorem A, let's say, which is due to myself, Ulmo, and Yaffe. So the original preprint was given in 2006. It was finally published in 2014. No comments. No comments. So it says the following. So let sigma be a set, not necessarily of special points, but a set of special subvarieties. In fact, these are two papers. So there's a paper by myself and Andre, and a paper by Andre with Ulmo. Set of special subvarieties in SHK, not necessarily points.
Andre is Andre, his first name is Yaffe.
So yeah, exactly. Yes, Andre Yaffe. So then assume one of the following. GRH for Dirichlet functions. So some arithmetic hypothesis. Or, well, I don't have much time, so there is another case where you assume that under some embedding of G inside GLN, the generic Mumford-Tate group, the generic Mumford-Tate group of the special subvarieties V lie in one conjugacy class, one G of Q conjugacy class as V ranges through sigma. And then the conclusion is that then every irreducible component of the Zariski closure of the union that is denoted by sigma with a double bar ZAR is special. And well, the case where sigma is a collection of special points is the Andre-Oort conjecture. Okay, so this is the first result, and I have to say that the proof is kind of intricate. So it uses ergodic theory, some algebraic geometry, and some Galois methods. And I should also underline this is completely based on the original strategy by Edixhoven. So based by Edixhoven. The next thing that I should mention, but I won't have time to talk about that, is that in fact you can remove the entire ergodic theory part. It was done recently by a student of Andre. And in fact, it was our original idea, but at some point we changed direction. But in fact, it can be done. And what you do for replacing ergodic theory, use a very powerful theorem of Prasad that gives you the volumes of quotient of arithmetic varieties, depending on the arithmetic type of the lattice. So in some sense, now the proof is completely algebraic. And then the second main theorem is a recent breakthrough by Pilar. Yes. Sorry? Yes, so I will explain, but these are some equidistribution results. So theorem B, which is due to Pilar, and I will, in 2010, I will not mention the most general version, but let's say the Andre-Oort conjecture holds and unconditionally for the Shimura variety, which is product of modular curves, C to the n, or any n. So at the workshop, I spoke a little bit about that. So I decided to speak upon request. Yeah, he's giving a talk also next week on some generalization of this. So, and here the methods are completely different. This is based on O-minimality and Diophantine geometry. I mean, the link between O-minimality and Diophantine geometry being given by this theorem of Pilar-Wilke that I emphasized at the workshop, plus the hyperbolic Ax-Lindemann conjecture that I also explained at the workshop. Okay, and so recently there was some improvement in the sense that now the full strategy works for any Shimura variety, except that we still need a good estimate on the size of Galois orbits. So in general, we still need GRH. So using this kind of methods, you can give another proof under GRH of this result. It's an improvement because here we use GRH 2 times and here only once. Okay. So now I want to say a few words in the remaining time about yes.
So I missed the n equals 2 case. That's also training on.
So yeah, it's highly non-trivial, but here, I mean, you do it directly by very special properties of the J function in some sense. And it's a very delicate Diophantine analysis by Andre that gives you.
Actually effective.
Yeah, it's even effective. Okay. So let's try to say something non-trivial about the proof. Okay, so the starting point of the proof is some alternative between ergodic and Galois methods. Well, let's talk first about ergodic methods. So why are they relevant? Well, the idea is that you want to control the Zariski closure of a set of special points. All those points are defined over number fields because they are special, and so you can take their Galois orbits. And the idea is that their Galois orbits will be very big, and you could even try to prove a better result than the Andre-Oort, namely equidistribution of their Galois orbits towards the measure of supported by a special subvariety. The point being that any special subvariety has a canonical probability measure. So any V special has a canonical probability measure, right? Because it's essentially, I mean, V is given by some Shimura datum HV and XHV, and some embedding inside GX, where you can even take for HV the generic Mumford-Tate group on V. And so this means that V is the image of some map which is finite. Some arithmetic, take the quotient of XHV by some arithmetic lattice, and then you have a finite map to the Shimura variety. Okay? Now the point is that this is an homogeneous space under a reductive group, and you take a quotient on the left. So here you have a canonical volume given by the R measure on the group. And so you just push the canonical measure here by this finite map, and so you get a canonical probability measure mu V. I will denote this probability measure by mu V, and it is supported on V. So now what you want to do is try to prove, if you are lucky, that when you have a collection of subvarieties, special subvarieties, then this probability measure will equidistribute inside the big Shimura variety. And this is what Clauser and Moll did, and it works in some special cases. So let me explain the result. what you do is that you fix a torus in G in the adjoint group, which is R anisotropic, and this is a Q torus. So its set of R points is compact. And you will say that a special subvariety is T special if you control if T is equal to the center of the image of the generic Mumford group under the adjoint map. Okay. So what you are trying to do is to control this torus, which is the image of which is the center of the image of the generic Mumford group. And the result that that Clausen and Ulmo prove is the following. So this is the following equidistribution. This is due to Clausen-Ulmo. Well, in the case where T is trivial and Ulmo in general. And this is essentially an application of Ratner's theorem in abelic theory. So the main idea is that on all these kind of homogeneous spaces, you can completely classify the probability measure, which are ergodic under the action of a group generated by unipotence. This is Ratner's theorem. And essentially, it tells you that this is supported by algebraic homogeneous subvarieties of this. Okay? And essentially, this is what gives, after some work, of course, non-trivial work, this result. So the result is the following. Suppose G is equal to G add. It does not change anything, because if you want to prove something is special in the Shimura variety for G, you just can map everything to the adjoint group, prove it there, and then because this map is reasonable, and everything is functorial, it will tell you that you are special already in G. And suppose that you have a torus G, which is as above, R anisotropic, Q torus. And suppose now that you have a sequence of T special subvarieties inside SHKGX. Then the claim is that if you look at the measures of these guys, then they will equidistribute. And in fact, there exists V, which is T special itself, such that mu V and K for a subsequence converge weakly to mu V. And more importantly, the support V and K is contained in V for K sufficiently large. Okay? So if you look at this result, this tells you in particular that the Zariski closure of this V and K has to be V. So in particular, an irreducible component of the union of V and Zar is special. Is T special. So this proof essentially is a conjecture, but only for T special. And well, the trouble is that, for example, points are very far from being T special. Okay, so some comments is that this does not apply to points, to special points, because if you fix T, there are only finitely many such points. There are only finitely many special T special points, right? They are just those given by the Shimura variety associated to T. We know this is finite. So this result tells you nothing for special points. And moreover, it's just false, which is even worse for special points. Right? I mean, you take a sequence of points. If this result would be true, I mean, in that case, for points, it's just a punctual measure. And this would just say that the sequence of punctual measures supported by those points converge to the measure supported on a special point. But it's, I mean, we know that those points are dense, so we just take any sequence converging to a point which is not special, and obviously this is wrong. Or you can, even in the non-compact case, you can make the sequence diverge to infinity, and in some sense, this is even worse. I mean, the measure is going out. Okay. However, this result is not optimal because we are not taking the Galois orbits into account. So there is a general equidistribution conjecture that I will not write into details, but basically that says that if you take the sequence of probability measures supported by the Galois orbits, so you take the entire Galois orbits, you renormalize by the number of points, then those things should equidistribute to the measure supported on a special subvariety. And this would imply the Andre-Oort, and basically the conjecture is completely open except in the case of curves. Okay. So, nevertheless, we use this result. So what is the alternative now? So alternative and reduction. So I will state first a rough alternative, and then maybe I will try to give a precise. So roughly, let's first assume GRH for directly held functions, and suppose you have a sequence Vn of special subvarieties. And let's take inside the same connected components, so fix a connected component that denoted by skgx of the Shimura variety. And suppose that I have a finite extension of the reflex field. Then I claim the following: at least one of the following occurs. A, either the probability measure converge weakly to mu v where v is special, and Vn is contained in V for n large, and so it gives you the answer. Or, well, and here a serious geometry starts. You can take the degree of a, so I will explain the degree of the Galois goes to infinity when n goes to infinity. So you have your special subvariety Vn. You take it Galois orbit, so it's a finite collection of irreducible subvarieties of a C. All this is inside the big Shimura variety, and the big Shimura variety has a canonical compactification, the Bailey-Borel compactification, on which there is an ample line bundle canonical also, which is Lk. I compute the degree of this finite union with respect to this line bundle, and the claim is that this degree goes to infinity. Okay, and which case occurs? Well, the answer is that it depends on the geometry of the Vn's. Well, for example, A occurs if the Vn's are T special for some given torus T. This is exactly the equidistribution result of Lausanne-Elmo. And B, for example, always occurs for special points. Okay, so so now let me try.
What is your assumption used with
This degree. I have to be sure that the Galois orbits are sufficiently big, and this will be provided by some effective Chebotarev counting, and this effective Chebotarev I need GRH. Okay, so let's try, and now I'm sorry, I mean the big mess starts because well, it's complicated. There are some notations. So what will be the notations? Well, you start with a special. There are a lot of invariants associated to a special subvariety. I will always assume now, and I can do that, that my compact open subgroup is a product of compact open subgroups at all primes. I can change the level because this Andre-Oort conjecture is completely insensitive to level. because of the definition itself of special. So it will be associated to some Shimura datum, HV XV, and where HV is a joint Mumford group at V. Then I will call EV the reflex field of this Shimura datum. TV will be the connected center of HV. So possibly this is a trivial torus. Then there will be the following arithmetic invariant. This is a product over all primes of the maximal compact open subgroup of TV at the prime P. So this is maximal compact of TV of AF. TV is a torus, so there is a unique maximal compact. So, and what will play a crucial role is the difference between this maximal compact and KTV. KTV is just T of AF intersected with the level K. Okay. Then there is the arithmetic invariant, which is the discriminant, the absolute value of the discriminant of the splitting field of TV. And finally, there is an invariant, which is the log of this discriminant. So this will be the important invariant. Okay. So well, now what is the theorem of about the size of these Galois orbits? The theorem is that first there is a lower bound for Galois orbits. Such as the following: assume GRH. And suppose you have Gx, a Shimura datum with a geojoint. And then, well, I'm sorry, it's really a mess. But you fix two constants R and N larger than 0. Then there exists a real number B, which is positive, depending only on Gx and R. And there exists a C of N, which is also depending only on R and N, such that the following is true. The big mess is that you have to prove that all the estimates are uniform in many different, with respect to many different variables. So let K be a product KP neat. Let's take V in SK GX C special and fix a field of degree at most R with F containing the Galois closure of EV. And then the estimate that you get is that under GRH, the degree for the Galois orbit is larger than this constant C of N, then you take the product, this is really terrible, over all the primes, such that the maximal at the place P is different from KTVP. Max of 1 and then B times this difference. I should have prepared slides, but it would have been easier, but I didn't have time. Well, anyway, it tells you that you have a lower bound for these Galois orbits. They depend on different things. They depend on what? They first depend on the log of the discriminant to a certain power that I can fix arbitrarily, because I can fix R and N as I want. And second, they depend on the position of the torus TV with respect to the maximal compact K. Because these terms, you see, I mean, the only places that play a role are the places where this maximal compact is bigger strictly than this one. Okay? So this is the estimate that you can prove. And under the assumption that the TVs are in only one G of Q orbits, you can get rid of GRH. And now, what is the alternative? The precise alternative so B, the alternative is the following: fix R, which is a constant here, such that for any age xh in Gx, sub-Shimura datum, there exists F, which is the field that I'm considering in this theorem, a number field with Fq smaller than R and containing the Galois closure of the reflex field EH. Well, this is not obvious that such a thing exists because I have fixed R once for all, but I claim it does. Maybe I should call this. So there are two parts in this bound, and we'll make a dichotomy on this. So let sigma set of special points, special v, sorry, in Sk, such that this quantity alpha v, beta v is bounded as v ranges through sigma. In other words, I'm just looking at all the v's such that alpha v multiplied by the log of the discriminant is bounded. Okay? And then I claim that I'm in the situation of Clausel and Ulmo. All these guys are T-special. And so I win. Then there exists a finite set T1, Tr of R anisotropic torus of G add such that any V in sigma is T special for some T for some T is equal to Ti. Okay? In particular, by the equidistribution theorem, if I am in this situation, I win. Okay? So this means that essentially I have only to look at the situation where the alpha v beta v is unbounded. And then I will do geometry. So what is the procedure? The procedure is completely different now. You suppose that the Galois orbits are very large. And what we do is an induction on the dimension. So this is the following result. Well, as above, we are in the same situation. We fix R as above. And suppose now that I have an irreducible subvariety in Sk of Gx. And suppose that Z contains a Zariski-Dense family. Sigma is equal to a union of the V of special subvarieties. all of the same dimension, it does not cost anything, of dimension n of sigma, such that the set alpha v beta v is unbounded for any modification. A modification of sigma is a subset of sigma such that the collection is still Zariski-Dense in Z. And then the claim is that under the usual assumption, GRH or the conjugacy class of the TVs, then and here really the geometry occurs. For every V in sigma, I pretend that I can exhibit a bigger, there exists V contained properly in V prime, special, and V prime still contained in Z. In other words, I'm out of V. If alpha v beta v is going to infinity, I create a bigger V prime. Okay? And furthermore, well, let's forget about, you have to prove that you can still not suppose GRH for this new family. Okay? So now the proof is clear. Once you have this theorem, take your collection of take Z irreducible and suppose it contains the Zariski-Dense subset of V's. So either alpha v beta v is bounded and you are in the situation of Clauser-Limo, the measure equidistributes to the measure of a special subvarieties, and this special subvarieties has to be Z. Or it does not, and then you apply this theorem. And this theorem tells you that for each V contained in Z, you create a V prime which is still special and of larger dimension contained in Z. So now you iterate the process with the family V prime. So what happens? Either those V primes have alpha V prime, beta V prime bounded, and you apply Clauser-Limo, or you iterate again. And well, by a Noetherian trivial argument on the dimension, this has to finish at some point. And in any case, it tells you that Z has to be special. Okay? So that's the alternative. So what happens in the simplification of the argument by Dou is that, well, basically you have to look at an invariant which is finer than the degree. You have to put some arithmetic information, more refined, and then you prove that this new arithmetic invariant in any case goes to infinity and applies the same kind of procedure for create new special subvarieties. So what can I do now? Well, so I wanted to explain the proof of this because this is really where the geometry occurs, where you create new subvarieties. So maybe I can try to give an indication of how it works. Well, basically everything is a game with Hecke correspondences. So the first thing that you need is a criterion to say that that creates for you a special subvariety. So here is the criterion. So criterion theorem A. Suppose you start exactly with this situation. V is special inside Z. And now you suppose that you have fixed your number field F. So this guy has to be supposed to be F irreducible. This means that it is defined over F. As an F variety is irreducible, but I look at its collection of C points. So this is no more irreducible over C, and this is in HKGX. Then the claim is that fix L prime splitting this torus TV and take a Hecke correspondence at that place. So in this torus. And then now I give you a criterion to say that there is a V prime bigger than V contained here. And the criterion is the following. Suppose that first Z is contained in its translate under the Hecke correspondence corresponding to M. And second, for any K, and now a group theoretic condition, for any K1, K2 in the compact, then K1, M, K2, the group generated by this element is unbounded. Is unbounded. then the conclusion is that then V is contained properly in V prime special contained in Z. So here there is some geometry, and the geometry, the idea is the following. Let's try to do that. The first thing that you do is that you use the usual monodromy results. So what you say is that you look at the representation of monodromy of pi1 of Z, at least the smooth part, and you know that this is Zariski dense in G, because you can suppose this is Hodge generic. You take the smallest Shimura variety containing it. So this is Zariski dense by Deling's theorem. And then now you take its L-adic closure at the place L. And because this is Zariski dense, this guy will be compact open. So this means that on the limit Shimura variety at the place L, the pre-image is stabilized by this compact open subgroup. Now the condition that Z is contained in TMZ tells you that this pre-image is also stabilized under one element of this form. Okay? So this is stabilized, Z is stabilized by a compact open subgroup at the place L and also by this unbounded group. Okay? So now you apply the group generated, which is not compact, to V. It's easy to see that it will create some V prime, which will still be contained in Z because by definition Z is stable under this. So that's really the idea. Okay, so I won't have time, of course, to give the entire proof, but I just want, once you have this theorem, I want to explain the analysis of the problem and how you make the induction. I won't be able to make the induction. This is a mess. So the next geometric part will thus try to apply this theorem. So analysis of the problem. So we have this collection sigma, and we assume that alpha v, beta v is unbounded for v in sigma. Okay. So what we want to prove? Well, we exactly want to prove to try to find such things: an L prime splitting TV and an M. Okay. So let's do the case, the simplest case. Assume for simplicity that the dimension of Z is just the dimension of any of those guys that I denote by n of sigma plus 1. In other terms, you have a hypersurface which are special. Okay? So we want to get one. What is the idea? We want Z contained in TMZ. Well, the idea is very simple. The idea is to exhibit an M such that the intersection Z intersected with TMZ is too big to be proper inside Z. Okay? So enough to ensure that Z intersected with TMZ is too big in the following sense. So suppose that M is in TV of QL and satisfies the following condition 1 prime. There exists sigma in Galois of Q bar over F such that when you apply this gamma element to V, then you are contained in TMV. So I suppose that I have an M and which satisfies this property. Now Z is defined over some number field F, this number field, so this means that the entire Galois orbit is contained in Z intersected with TMZ. Okay? Here, of course, this is TMZ. Fine. Okay? If I have just one translate by Galois, because everything is stable, this means that the entire Galois orbit is contained in the intersection. So now what we do is that we look at the intersection and we compute its degree. So if Z intersected with TMZ is a proper intersection, what do we get? Well, we can compute the degree of this Galois orbit. Okay? And because I have the fact that it is contained in this intersection, this will be smaller than the degree of z intersected with TMZ, which is the degree of z square times the degree of the correspondence Tm. But the degree of the correspondence Tm is KL intersected with MKL m minus 1. Okay? And on the other hand, here I have the bound by the previous result. I know that this is larger than C of n alpha v beta v to the n. Okay, so now what is the game? The game is to exhibit an m, first an L, then an m, such that this is smaller than this. If this is smaller than this, it tells me that this intersection is never proper. So m has to be contained in TMZ. Okay, so this is the idea. So the result of this analysis is essentially that we have to produce two things. Donc the lemma is thus, after this analysis, is that suppose that there exists L prime splitting TV, such that, in fact, what we will do is that we will decouple the problem. Here there are too many variables. There is L, M. I want to decouple first, find the M, and at the ultimate end, find the L. So to be sure that for every L there will exist an M, and then find the L. So suppose that so this will replace this term, and this is the term on the left. So suppose you have this, and suppose you have B, that there exists an M satisfying the properties that I want. TV of QL, such that there exists sigma in gal of F bar over F, such that sigma of V is contained in TMZ. This was my first assumption. Second, I want to be sure that the term on the right, which is KL m minus 1, is smaller than L to the K. So if we have this condition, and if I have this condition, I have that the term on the right is certainly smaller than this, so I win. And second, I want to apply this criterion, so I still have to be sure that this condition is satisfied. For any K1, K2 in KL, I want that K1, M, K2, the group generated by this element, is unbounded. Then I win. Then there exists a Z prime. I can, by this analysis and applying this theorem, I get that there exists V prime special bigger than V. Okay, so I don't want to be too long, but this is really what this analysis leads to, at least when the dimension is just one more than the dimension of the special subvarieties. In general, you have to iterate this procedure and be much more careful about the bounds that you get to be sure that after dimension Z minus dimension of V iteration, you still get the right bound to apply this result and be sure that it works. So this is really disgusting, but I don't want to talk about that. But now here, what is remarkable is that you completely decouple the problem. If you look here, you fix an L and you want to prove that there exists an M satisfying those properties. And this is a pure problem in group theory at the place L. So this means that this is a problem in p-adic groups. And in fact, you solve it by looking at what happens on the building and the dynamics of those elements. Okay, so this is purely group theoretic. And it's a nice criterion that such things exist. And then at the end of the end, you have to find a prime which is small in some sense, very small. And this is why you need effective Chabot-Arif to conclude the proof. And to have effective Chabot-Arif, well, you need something. So, for example, GRH for Dirichlet function, or under the conditions that we put, in fact, effective Chabot-Arif holds. If we, in addition, we ask that all the special subvarieties have their general Forte group, which are in the same G of Q conjugacy class. So this is basically the strategy of the proof. I don't have time, I'm sorry. I spent a lot of time on Shimura varieties. Probably it's more important than this, so okay, I will stop here.